Hello everyone, we are starting the stream very shortly. I'm just setting up my lights because otherwise it will be pretty hard to see the components. Okay. We're almost done here. Anybody who is joining, please join me on Discord. If you join me on Discord, I will be able to talk to you and you can ask live questions. So all right, we're ready to go live. Okay. Camera. You can mute me on Discord. Oh, no. You should keep my audio on Discord because then you can hear me live, but you can see me with a little bit of delay on the stream. Hang on a sec. The camera feed should start coming in now. No? What happened, bro? No, the background camera, as in the main thing that shows me blank, as in black, dark. Yeah, give me a sec. Let me try and address what happened here. Okay, we're back. Yes, that's all it needed to be done. Cool. I think I need to manually refocus it again. Is that better? Yeah, it went a little too far. Oh, okay, let's start with this. Holy cow. Cool. Chicka chicka bow bow. Cool. Okay. So this is one of my old laptops mother. Using something that I already have because that makes it more relatable. Let me get us something to point with. So swipe it from the part that is more common to us so that we can eventually get to the point that is less common to us. So I'm not getting the disassembly part and all. I think I'll make a video about the disassembly that I did a few days back, not a few months back essentially, and it's still lying around like that. So easy part is this is processor. This part is the heat sink essentially that is taking not only the CPU but from North Bridge as well. I'll come to that what is North Bridge and all in a moment. But so basically this is the part that this is a copper tube that is taking the heat from all these places and spreading it over here. Fan used to be here. I have the fan somewhere over. Okay, let me give me a moment. So here's the fan that goes in there like this. So so it's effectively this fan. It's another thing. Nothing about motherboard or something. So you can see this fan, this kind of fan. But Nine International Baba, Mo. So these fans don't have a push or pull configuration. They are flat fin fans. What is happening here is hello Walter. Right, hello Walter. So what happens in here in these kind of fans, they are not pushing the air from from this side to this side or from this side to this side. Instead, what they're trying to do, they're pushing the air through this vent. So whenever if the fan is inside here and the area inside is getting hot, that means that air expansion is there. The fan is going ahead and pushing that air through, as in the air is naturally expanding. The fan is just letting it pass through from these vents. That's what is happening. That's how these fans work. Anyways, the intake of the fan is, so whenever the fan is like this, the entire upper portion is the intake. It does not matter. It doesn't have to take from some wherever the air pressure is. So hot air will expand inside the mother as in system, right? So whenever the hot air expands over there, so it will have more pressure than the outside air over here. So it will naturally want to go that way. The fan is just directing or like pushing that air outside. And yes, and the motherboard will have other vents or as in the openings on the other side that will push the air in to rebalance that pressure. So that's how it's working, and which is why if you put the laptops on any kind of book or on the bed that blocks those vents, then the cooling goes haywire because of that reason. So yeah, that has nothing to do with motherboard per se, but this is one of common mistake that I see a lot of people do, putting laptop on books or on bed. It will actually soak in the dust from the bed surface as well. So that happens a lot for people, and the entire thing will be messed up. So that's how it is. I might actually go ahead and open up the CPU here in a moment, but so far I haven't, just so that to keep it pristine. Do I go through the like ports? This is a little bit older motherboard from 2007. So there are some things that we don't see anymore. The older stuff, like let's say the phone port. You could actually use regular phone connections over here, and the motherboard had modem that you could. Motherboard inside has a modem. I can show you if I flip it over. No, I don't have to flip it over. So this part, this particular section, if you can see well, has a block cut out, right? So this wire that comes over here from this side, this wire goes all around here. So this is that modem, the connection that goes from here through all the way around to this section, and it actually, so that it is separated in the isolated in that way so that it doesn't interfere. I'll come back to those topics afterwards. But the point here is it had directly the phone port along with RJ45, that is the normal LAN port. This is not gigabit or anything. 100 Mbps was more than enough at that point in time. This is the power port. I'll come back to power again. I'm just gonna give a rundown on the ports it has. These are USB ports, USB 2.0, USB 3.0 wasn't there yet. Uh, those ports. These are the yeah, these are the audio in and out, as in mic and stereo audio. Then this one is the SATA port. So this had a 2.5-inch spinning hard disks. Like spinning hard disks, 2.5-inch were the mechanical hard disk. So those were the new things at that time. So this was pretty kind of bleeding edge for the time. SSDs were not a thing and laptops were trying to save. Yeah. So SSDs were not a thing, and laptops before this generation laptops were also, most of the laptops were using that 3.5-inch hard disk, the bigger hard disk, the desktop hard disks. So this is called like a different specification micro SATA port. So micro PATA port. So this is actually not a serial interface. This is a parallel interface, and this one hosts the disk drive, the CD and DVD drive. That was actually on PATA board. This is not SATA, and I actually have that drives isolated. So I was trying to salvage that, but because the interface is so damn weird, if it had normal PATA port, which goes something like, give me a moment, which is something like this PATA port, right? If you had older PATA hard disk, like parallel hard disk, that's what it used to look like. SATA is connection is really different. So if it was like that, a normal PATA, I could have salvaged that drive. I could use that for a different purpose. But I think I'll just open it up as in do a tear down of that one, salvage the laser and salvage the lens that it has. You can actually use that lens and use it on top of your mobile camera and do macro shots, like use it as a microscope or something like that. You can go get a really good magnification, right? Yeah, yeah. If you have very old CD drive or DVD drive lying around, you can actually use that for this purpose. It's really good that way. The lens is really good and the laser is pretty good as well. Anyway, so I so basically as it goes that I cannot use that drive for anything at this moment, and it's also the interface is not that fast. I cannot really read DVDs with it. It's just so essentially like a lot of things that makes it way too old for being used in 2021. Anyway, so this is the power port that comes from battery. So these are basically, two of them are positive, these are grounds. Meanwhile, temperature and amount of power, as in the sense how much power you have left in the battery, those kind of sensors are in the middle. This is the 6 port. These are not the connectors that we use as a consumer, but these are pretty much standard connector for OEM and vendors, manufacturers, the people who make motherboard and buy battery packs from others. These connectors are for like them to understand. Like we don't have to use those ones, but these are pretty standard thing. Like the one USB is standard for us; those are the standard thing for them. So uh, there's another thing over here that is, if you see this particular thing, it hosts a mini PCIe slot. This is a mini PCIe slot that goes up to there. So this section, like you can bolt them down over here, and that was the Wi-Fi card. So the board, even new boards actually do not have onboard Wi-Fi because of the interference. The same thing that I talked about, touched on a little while back. So because most of the wireless communication relies on very fast like megahertz and gigahertz, like the 5 Wi-Fi 5G that is works on 5 gigahertz band. So those frequencies interfere with the actual signal traces on the motherboard. So it's actually preferable to have it on a daughter card than having it on the board itself. So that's why most of the time you will find even the newer board, the newer motherboards, or even the desktop motherboards that has Wi-Fi cards, it actually is hosted on a daughter card on the top of the motherboard somewhere, like the on the CPU socket, other part of the CPU socket, on the IO shield, on the top of the IO shields, somewhere hidden. People don't get to see it directly, but it's actually not. Most of the time, it's not on the motherboard itself because of that reason. So I'll come back to those things. This IC is pretty interesting as well. But anyways, so that's what is hosted over here. And mini PCI is actually a very nice standard. It was, I would say, nice, but it tried to do a lot of things. And at that point in time, it actually got it done. Like it was doing, not only it had one PCIe then, plus it has native support for reading SIM cards. Then what else does it have? I keep on forgetting. It has a USB LAN, and one other thing I keep on forgetting, like most of the stuff we don't use them for anyway, but so basically this one thing gives a lot of stuff that can get a consumer system, um, make it a better consumer system, and removing this entire different footprint if the vendor doesn't want to give one extra peripheral, and that peripheral supports most of the stuff you need. um anyway, so that's on this side. Let's flip it over. And actually, the way motherboard, laptop motherboard vendors work, they actually put components on the both the sides, because they can. Oh, by the way, there was a display connector over here. I was salvaging a IC from this section, so while trying to desolder it, I actually ended up desoldering the display VGA connection as well. It fell off. uh, I was actually taking out, like replacing this particular one, this MOSFET over here, with this better one. So I did that. So power I fixed, but yeah, I'll come back to it. Anyways, so this is the internal display. This is called LVDS. Um, LVDS. Would it help if the terms that I'm mentioning, if I show a little bit of like Wikipedia page or some other references that helps understand the things? Because some of the terms might, I'm saying LVDS and I know what it is, but probably you would want to know more. Yeah, exactly. That makes sense. Yeah, I would expect that, but yeah, that would be the ideal thing to do. But okay, cool, good to know. I prefer that way. Cool. So that's the LVDS. So LVDS is basically in all the monitors, pretty much all the LCD TFT monitors that you buy. It actually basically works on this interface, to actually send the display on the screen. So the monitor itself has a motherboard. Once it's sending the display through a HDMI or DP or any other uh, the display information, it needs to go in. And give me a moment, I'll show you another thing. So okay, quick jump on a different topic. So once the information comes in through, this is a old monitor's motherboard, very old monitor's motherboard. Okay, so the information comes in, the video information, video buffer, essentially that's what is called, well, graphic card, whatever that is pushing, right? So the video buffer comes in through whatever the interface. This is the analog interface, but you can have digital interface like HDMI, DP, or whatever that is. That comes in, goes to, this is one chip, this is Samsung's. So this is actually pretty good board. I'm trying to reuse it. Anyway, so that comes over here. It passes that information into actual line by lines, the pixel information that you have. If it needs to count, how do I see? Okay, so from this side, right? From this side, 1 2 3 4 5 2 19 20, and then second line doing that 1080 times, right? 60 times per second. That's what is happening over here. So every pixel, counting every pixel, and then determining which color to draw, essentially, because display is very low level. It doesn't understand vector and all the other kind of thing that graphic card understands. So my phone is dead. We cursed it last week. What happened? Oh God. Yeah, you talked about your phone. uh, I'm sorry to hear that, man. Do you have a replacement? By the way, I'm on Discord. I posted the link. Join on the Discord channel. I'm waiting for you. Anyway, so got new phone. Which one? Anyway, so oh, cool, cool. Come on, voice, man. Come on, voice. So Gautam is posting on Twitch chat. So I was replying to that. Yeah. So yeah. Nice one actually. So where was I? So the graphic card understands the information about the triangles, the shaders, etc. But then the graphic card boils it down into RGB information. the raster, like the per frame buffer. It's called frame buffer in itself, right? So it is actually sending one frame at a time, the entire 1980 by 1080, sorry, 1920 by 1080 or whatever the your resolution is. That information is being sent to through this port, and then the job of this IC is to take that entire frame information and boil it down to per pixel information and then send it through this interface. So this is the LVDS interface. This is called ribbon cable interface. So FPC, flat cable, flat panel cable, FPC, FFC. Well, anyway, so that through that interface, the actual monitor renders what you see on the screen. So this is the LED controller, the backlight controller. Anyway, so I'll set this aside. This is not too much, this is not too confusing or anything. This is pretty simple circuit, mostly pretty simple circuit. Anyway, so I'll set this aside for now. We'll come back to it. Anyway, so that's the interface over here. That's the internal display, and I showed you the other display as well. This is the keyboard, and this is the touchpad. This is this is the ribbon cable interface for the keyboard, internal keyboard, and this one is for mouse. I'm showing it this way for other different systems, the different motherboard, different vendor. It will change, the form factor size will change, but the concept is pretty much similar. So these are the components you expect to see, and this is how you expect to handle them. Sometimes you'll see that some components are not populated. Like let's say this is like seems to be some kind of another APC, like one of this, and those are basically because when vendors create new design for the motherboard, right? They create for the comparative, like closer models. Let's say Dell XPS 13. One is the normal HD version, one is 4K version. So that needs the different kind of so different SKU for similar product. So they create one design because that's cheaper to do that way. So they create one design, but they don't populate all the parts for the other components. So they save this cost. It's easier to do it this way than to design three different motherboard layout. Yeah. So even though it seems the other way around from outsider perspective. So that's it. So this is the peripheral part gone. Now let's go down to the actual business. We all know the RAM. So the RAMs are pretty easy, right? This is the CMOS battery. Nowadays CMOS batteries are a little bit different, but you can still expect to see this thing on different models. So with that said, which one should we talk about next? Do I talk about how the this chip's interfacing goes, or do I talk about, let's say, how the power goes, or wireless or network works? Which one do you want to hear about first? Processor? The mhm, mhm. Even now we have what? Yeah. Even now we have Wi-Fi card only. As I said, Wi-Fi is almost always are on a daughter card. It's not on the main board itself. Um, so actually it goes pretty much all the time on the daughter card because you don't want the noise of it's not a noise, it's a signal for the Wi-Fi, but the traces that are carrying different signal, for them that other signal becomes a noise. Think about a market, a fish market, right? You are trying to have a conversation with one person, and whatever you're saying is it makes sense to you and to that person we are talking to, but because there is so much noise around, you have to shout, right? And because of that, the person beside you who is trying to have another conversation with another person, he has to also shout, because whatever you're talking about, even though it makes sense to you, it doesn't make sense to them, like for their conversation. So now to make their point, they have to shout, and so that they can hear each other. So in that sense, it becomes noise when you have this, same trace, same board. So if you can understand this, all these small things, right? These are all capacitors, resistors, and all these things, and traces are going, the copper traces are going from here to there and all the other places. I'll try and cover that power, at least the power plane, how that works. But so that's all there are. So if you have different signals, especially something that can cause noise, radio frequency and above, that breaks down the entire thing, especially the processing, the compute. So this particular path is a very high frequency, high, like, sophisticated communication channel, and you don't want any noise into this. So that's why you keep this separated. So let me do you have mini PCIe? Do one thing, Google's image search mini PCIe pinout, something like this. I'm gonna post it on this chat. IE pinout. So look into this and you will see what are the things that it is doing. Let me also try and open, sorry, in a proper manner. For me, the first one is fine. So you can see some of the pins are reserved. Some of those pins are used by the vendors themselves to write custom driver, to find a custom device, etc. All those kind of stuff. But other than that, sorry, except for the reserved pins, you will see these specific ones, the either PERN0, PERP0, and PETN0, PETP0. Basically, TP0 and TN0, RN0, RP0. Those are the, like, transfer and receive lines of PCI Express. So essentially, how high speed communications work, that includes the LVDS, by the way, the display thingy. This is very high, that is very high speed as well. So they work in a, it's called differential signal. So similar to USB, if you see in USB there are four, like USB 2.0, there are four teeth, right? And what are those four teeth doing? One is 5 volt, one is ground. So those two are power. So if you short the other two, those two will give you power. No data, just power. But the middle two are data, and middle to our data, they are not only kept here for any kind of specific purpose, they are actually kept together throughout until the termination of the connection inside the motherboard, wherever they end. And especially if they take any turns or something, the inner connection is made a bit longer to match the length, so that two, actually, instead of sending a signal over one connection, we're sending it over two connections, and in a differential manner. So one, if the one is high, then other is low, right? So what happens if a noise comes in, the noise affects both the signals in a same manner. So if you minus one minus the other, then you get the actual data. Instead of reading the value of one signal trace, you read from both the signal trace and do this minus this. So if, let's say, one of the signal, you will just look for the delta, and the delta will always be 5 volt essentially, right? So, and either it will be plus 5 volt or it will be minus 5 volt, and that's how you're translating that into one and zeros. Okay. So that's what is happening, and that is true for not only USB, for any kind of differential and high speed signaling. So when you say PCIe 16x or PCIe 8x or 4x or 1x, that means that those many differential signals are in there. Those many differential, those many pairs. 16x means there are 32 pairs, as in 32 16 pairs, 32 communication channels, they are doing differential signaling for 16 different things. um, Actually 32, because one is transmit, one is receive. That's what you see in the T and the R. So in the, even in the differential signaling, right, one is only sending the message, one is only receiving the message, so that neither of them are blocking each other, and it can be duplex, full duplex. When sending the message, you can still receive message. So that's what is happening over here. So that's one thing. Then you can see the you can see USB D plus, USB D minus. I don't know which one particular one you are was seeing. If you are, um, yes, yes, and there will be SMB, CLK, SMB data. So that is the SIM clock and SIM data. No, that is not SIM clock SIM data. That is SIM clock SIM data. Yes, and the 3.3 volt that goes in there as well. And actual ref clock, SIM and clock, those are separated. Those are within the first key, the first slot, right? That goes in there. Anyway, so that's how mini PCIe was trying to associate a couple of very necessary thingies. And that, by the way, that USB interface, that is not actually one USB interface, that is actually opening up for a USB hub. You can take that USB interface, split it into 4 USB ports, and now that system has 4 USB connections. You can attach the keyboard, mouse, a webcam, and a pen drive, something like that, right? So, and all those things will work. And back then, at that point in time, that was massively cost reducing and convenient solution, instead of trying to address it in different other manners. Okay, so is there anything, is there any confusion that you have? I can actually show you the card. You can check for it. I have it here. All right, so this is the card. It goes in here. I like labeled it up. This is nothing. This just has what do you call that thing? I don't know. Open it. Yeah. So you can see I just labeled it up because I know I want to read the specification after. If you lose that information, right, it becomes very difficult to find out the information about that product, because as you can see there are lots of data lines, etc. I need to find out if I'm like putting it on a custom chip or something like that. I need to find out that how it works, etc. to read their information. I am not afraid to show the details because yeah, what are you gonna do about it? This is pretty old shit. So this is actually the one that was there. I salvaged it and I'm gonna use it. Um, I'm gonna use it with. Okay, so I'm gonna use it with a PCIe expander, so PCIe 2 mini MPCIe card, and use it on my old motherboard that doesn't have Wi-Fi built in. Anyway, so do you unless you have any specific questions, I will move on to the next one. Do you have anything? Ah, so M.2 is actually quite different, and the easier way. So this should be your pretty this should be your takeaway. How to find this thing? Do one thing. M.2 ngef f pin out. Search for this. Sorry, M.2, not M2 dot. Uh, so thing is, if you want to know more about the components, right, looking for pinouts always is the better solution, because thing is, unless you are NGFF, not NGEFF, that's also another thing. So unless you are um, somebody who is working on it on these technicalities, nobody is actually looking for M.2 drive picture by searching for pinouts. So add the term pinout and you will actually get a lot of more details, extra details about it. So that has M.2 has similarly assembly clock as well, but SATA A plus, SATA A minus, both there's SATA has two differential signals, SATA A lens and SATA B lens. So two differential means total four connections. So that's what it basically implements. It actually can have, it actually has enough space for more than that. It can have about 4 hard disk connectivity, like 4 sets of, so basically 8 lanes, but basically most of the time it just has one if you are using one. But sometimes some of like my motherboard supports 4x. You can have 2x or 4x connection as well on the M.2. In that case, it's actually using 4 times the data bandwidth than a normal hard disk would. Do you see the pinout? Is there on Wikipedia page? The pinouts are there. Go to image search. Go to Google, do the exact same search, M2 NGFF pinout, and go for image search. You will see the pinouts. You will see that there are lots of NC. NC means not connected, and that they're not connected not because they should not be connected. It's just that you can connect them if you want to for specific purposes. So sometimes the vendors choose their, most of the time nowadays, of course, almost all of them, especially like let's say if you're using high performance M2 drive like Samsung Evo or something like that. So they will definitely implement 4 lanes so that you can get the maximum bandwidth possible. So it will use. Do you see that SATA plus, SATA A plus, SATA B plus, SATA A minus, SATA B minus? So that whole thing, those four traces will make one hard disk work. So four into those many would be there to give you the full interface like at that high bandwidth to connect it. That's why M2 drives get that much high bandwidth. But the pinouts are not the same, by the way. Pinouts of this is not the same with the mini PCIe pinout. This is not the B key. So most of the time, so you should probably search for M key because that's the one we use. B key NJFF, that is the mini SATA interface, that is the lower performing version, 1 lane thing. So as it happens is that there are lots of different technical interpretations that come up, like people build the tech demos and some of them end up becoming standard, some of them don't actually become standard. So it's like that. The B key, M key is almost like that. So M key became more popular because it had the province for having four like interface, 4 different hard disks interface, SATA interface, and multiplexing all those things together to use one high speed flash drive, but using that with 4 SATA interfaces to make it faster instead of having it bottlenecked. So most of the time we are using the SSD 2.5-inch SSD. They're all bottlenecked. They can work much faster than that, but because we are using that with one SATA interface, they're capped at SATA speed, right? So that's why M key became more prevalent than the B key. And because B key has only one province for only one SATA interface. So don't confuse between the mini PCIe and what do you call that thing? The M2 slot. Those are different things. Not entirely different things, but conceptually similar, but not like you cannot slot one thing into other. Okay, yeah. So yeah, you cannot slot one thing into other. Similarly, you cannot put a SSD into this. It won't work. So this is the processor. So this is one chip. This is another chip. This is another chip. Right now in 2020 or 2021, it doesn't matter anymore because this architecture does not work anymore. Intel has moved on from this. Previously, there used to be three different main chips that made the entire system work. This is the main FPGA field programmable gate array. That is the main computer CPU that we call it. And the other two came with the motherboard. And we call them North Bridge and South Bridge. They have their own dedicated purpose, what they are doing, etc. I'll come to that. But so Intel came up with this architecture. They worked with it for a bit, and then during that the core era, the core duo, core 2 duo, and then core i5 when they was first started that thing. I think during the core duo era, they dropped this. No, core duo was still having it. During that core i5, i3 era, that's when they dropped it in 2010, 2011. So instead of having these two, they came up with one thing that is basically a bigger South Bridge. And North Bridge got integrated into the CPU itself. So previously, if you open an older motherboard, older as in something that is before 2007, 2008, you will see one main CPU that has a heatsink on, but two other things that has smaller heatsinks on. Those two are these ones. And if you find a newer motherboard, and though that motherboard will have only one. So the older generation motherboard had this interface that's called front side bus, FSB. What it is doing, it's a very fast, at least in that sense, that time's say it was let's say 533 megahertz or something. That used to be way too fast. Interface between these two chips that talk data only the compute, nothing else. It like CPU does not want to be bothered about smaller details, right? So let's come from the back side so it will be easier to understand. So South Bridge controlled most of the peripherals, like all the keyboard, mouse, um, other different cards, etc. All those things, like uh, if you have a SIM card slot. I think I didn't show you, I forgot to show you. This thing actually had a proper slotted uh, key card in slot in, and that was popular back then at that point in time in the corporate world. We don't use those things anymore. So those kind of peripheral interfaces, all kinds of peripherals are basically monitored and acknowledged by South Bridge. And the North Bridge is the higher speed, not really peripherals, but the components. Let's say the graphic card, the RAM. So basically, the RAM is coming through this and then being used by this. So you can understand why Intel dropped it, because it actually kind of works as a bottleneck. So all those like graphic card, RAM, and all these things are basically sharing one 533 megahertz lane over here, and they're bottlenecking each other. Not a good architecture, right? When it was started, it was not much of an issue because things were pretty slow, laid back by then. Yeah. So at that point in time, it was fine. It was good architecture because you're delegating different tasks to different components. It was good. It was easier to manage and stuff. But then in newer generation, it's actually a really bad idea to bottleneck things like that, because graphic right now, the amount of graphics data that we are pushing out, or the data that your CPU is communicating with the GPU, that alone would saturate this bandwidth. Forget about RAM. So CPU cannot use RAM at all. I mean, like, they're practically impossible, but think of it that and in that manner. And if it's using RAM, then it cannot use GPU. So that was the setup back then. Now we have dropped this thing in favor of and this interface between North Bridge and South Bridge was called DMI, a direct media interface. I think that was the name. I might not be entirely correct, but that's DMI is I cannot recall the D. It's most likely a direct media interface, but yeah. Nowadays, you only have the CPU and the DMI, the very fast DMI, with the chipset that is included. Right now, let's say if you buy Intel, you will get Z470, Z570, something like that. My older one is the Z270. Those are the chipsets. This is basically the South Bridge, a glorified version of the South Bridge. And what it is doing, it's doing the pretty much the same thing. It's handling the peripherals, and even now the network, etc. Previously, the network, etc. was handled by the North Bridge. Nowadays, that's also falling into this part. But CPU can now directly talk to the graphic card, RAM, and all these things, good stuff, without bottlenecking each other. And that's a different interface that it uses. So I am not gonna go into that details over there because it actually gets really crazy. How so? Easy to explain part is that it uses the 16x that we assign to the lanes, those lanes, right? Uh, to the graphic card. It can use 4 lanes for talking to a SSD into SSD directly. Yeah, and it has dedicated lanes for the RAMs. Most of those communications are on SPI uh, protocol, so basically serial interfaces, very high speed, very high frequency. um, Most of them, almost all of it, is differential signals, so that's why CPUs need so many thousands of this thing, what do you call it, the pins and sockets, etc., because it needs those many signal to take in. There's actually very much of a necessity. It's not that they're doing it for fun. If they could reduce the number, they would probably do that. um, yeah, so thinking of removing this, should I remove it or should I not move to next motherboard or explain more further details? I I mean, just opening the CPU, but I'm pretty sure you have seen a CPU, right? I'm like, I'll just let it be for the time being. Like, there's no point. Exactly. So this is pretty much boring stuff. The part that I was trying to go on and talk about is that one thing, most of us don't actually care about, but this is actually fun to know and try and figure out. Is that okay? Let me put up something behind me for the time being. I think I showed that last week as well, but did you? I don't think you've seen that data sheet. Okay, give me a moment. I will find out the exact spot. Okay, cool. Hmm, interesting. Okay. Um, I'm opening it on Edge just because I don't want to open other browser sessions over here. So here is the specific, as in the power rail, how the power is getting into the system, how that, so basically this is how the power is getting into the system, being broken down into parts, and then how some part is actually going ahead and charging the battery, and which part is actually going into make the as in system run, which part is going to the system run. This is actually wrong. This is actually going for the system, and this part is going for like, oh, this is coming from the battery. this is coming from the battery in case the actual power, main power is not available. So these ones. I know that you're a little bit lagged, but the part that where you see the bat written, right? So those ones are the battery inputs that are coming in to power the system when main voltage input is not there, which is the AC input is not there, essentially. It's not AC, it's DC, but anyways. And if the AC input is there, right, then sorry, on mobile, এখানে. So if the AC input is there, then it will go on and power the batteries instead. Uh, I'm pretty sure this circuit is missing something. Oh, okay, yeah. So yeah, so this is the main power section from here, from here. This comes over here, and then it actually gets into the system and powers the system. Anyways, so main point that I'm trying to make here is so the main point that I'm trying to make here is that when you get the power in, the power is actually getting distributed from these things, from below the surface, from like there. Yeah. Oh, okay. Yeah. Sorry, my bad. I'm gonna rotate this thing. See. This is the power port. This is the power port, the AC jack you put in, right? Power adapter jack. And after that, these are the MOSFETs, and this is a diode. So what these are doing, these are ensuring that it doesn't feed the power back. So at least the diode is doing that. Because think about voltage, it's in the sense of pressure, right? Causing pressure. So if one side has pressure, one side doesn't. Like let's say you have the battery in your system. Now the power is cut. Suddenly power goes off. That means this voltage source does not have a voltage, but this internal side does. So what it will do, it will feed the power back outside in the power brick. It will try to cause a circuit, try to create a circuit from this side to the other side, like the other way around, the reverse circuit, right? That will damage the power brick. So you want to avoid that. So that's why it has a diode, and diode lets power go in one way but not the other way, and all this kind of good shit. So anyways, so it's going in here. We cannot see what is happening on the paper trace, so it goes down below. And this motherboard, even though it looks very thin, right, looks very thin, it actually has way too many layers into it. My coffee is here, thank you so much. Standard practice is say 16 layers. Most of the complicated boards are 16 layers, but sometimes I'm pretty sure these laptop boards are probably fine with 8 layers. I wouldn't expect them to be 4 layers, but most of the um, DIY community, let's say that add-in board, the daughter cards, etc., those are most of the time 4-layer boards, and all the much easier, rather easier circuits like the modules that you buy off of eBay or AliExpress, a LED circuit board or something like that. Those things are basically just 2 layers, right? So it's actually easier to manufacture. The number of layer increases, the cost increases. But uh, anyway, so where was I? I was showing over here, right? So power actually goes down below from the internal circuits because you have to take in the connection over here, and that goes over the main upper layer. power goes in below, comes up over here. Here it gets spread around, as in divided into multiple parts, as you saw in that circuit, right? Then from there, think about this. From here, from actually from through this way, it comes to this battery and charges the battery. So yes, one of the middle layers. It's happening on one of the middle layers. Also, the battery is now. Uh, this is another power management IC over here, and so, and these are the inductors. These are basically nothing but a coil. Coil is in, there's a magnetic core, and then there's some wires, wind like some similar to transformers. So these are called inductors, right? So those are there, and then the other side, these are all. This is all the power management. The entire circuit that is seen there. This is half the part of it, and then it again comes up from this side, from this trace. I don't see if you can see the color differences between this and this. This is deeper. This is deeper blue, and this is very lighter blue. So this trace, okay, let me see. From here, this section that goes in here through this. Over here is a deeper color, deeper blue. Do you see? And that part is actually avoiding the CPU, main CPU. The power part is actually avoiding the main CPU, which is here. So this deeper blue is where the trace is not there. The lighter blue is where there's a copper trace in between, and because it's a high amperage line, this is basically about, let's say, charging the batteries from coming battery. So almost for 18 volt and 3 amps, 4 amps line that is coming in. So they made it thicker line. So comes in over here, and this is again a power trace, and this is distributing the power to the components. Like some is going like much of it is going to the CPU. This particular circuit is actually monitoring that part. These ones are actually sending it back to again the peripherals, and then once it goes there, it gets divided into smaller voltage. So system cannot utilize that 18 volt. It has to break it down to 12 volt and 5 volt and 3.3 volt and then 1.8 volt, 1.2 volt, and all these different kind of specifications for different purposes. Like CPU uses 1.2 volt or 1.1 volt, something like that. RAM uses, like depending on the generation, RAM keeps on changing, like lowering their voltage, but again something like around the 2 volt range. So those conversions has to be there, and that's why you see those inductors. Inductors are basically uh, wherever you are seeing those inductors, these ones, the coils, right? These coils, that's where the power transformation is happening here. These are also inductors. So those are all the places where power conversion is happening. There are also capacitors, but they're less prominent. These are the capacitors. Okay. I'm pretty sure the lag doesn't help, like the video and audio lag, but I could find out a better way. I'll try that next time onwards. Okay, cool, cool. Already know about. Okay, so let me just so quickly touch on the some of the other key components over here. So there are these bigger ICs, these ICs, these ICs. These are all like, I can tell you what they are, but I would rather tell you, instead of giving you the fish, I would, oh, you made a tuition. I would rather teach you to fish so that you can fish for yourself. So whenever you see see an IC, right? The IC, this is one thing about hardware industry that I like and love, is that they're very good about the nomenclature, or no, not nomenclature, but at least the specification. Each of the numbers here have some meaning. So if you search for CB-141GB, you will find out the details about this particular IC, what it does, what is meant for, what are each individual of these 64 and like 256 pins are doing and all. You will find out all the information about it. That's one thing that hardware industry does very well. Unless something is under NDA or anything else, but so you can go ahead and always look into those things and find out what it is doing. So if you are stuck with, let's say you are trying to diagnose one of your motherboard and there are some problems, you cannot really figure out what to do about it. You can try and figure those things out that way. So how I did it, like what happened in here, what was the problem in this motherboard? I'll touch that one first. So my motherboard had power issue, like a really big bad power issue. At that point in time when that happened, I knew nothing about this, so I just kept it as it is. The computer doesn't work, but I didn't want to just throw it out. And like, okay, I'll figure it out one day. So eventually I did figure it out. I just figured it out that it's unsalvageable. Like to the point, it's totally unsalvageable. To the point, the speaker port, this goes to the speaker, right? I tried to salvage the speaker as well, but even the wire inside the speaker is burnt up. It had some kind of a surge that totally burnt all the circuits. The battery circuit was burnt up. Batteries were good, and in fact battery was being reported as bad, but just because battery circuit, the protection board, that circuit that charges the battery and stuff, that part got fucked up, but actual batteries were good, are still good, and using it. There are four batteries that I'm going to make a power bank out of. So yeah, sometime soon I'll do that. More than almost 14-15 years old batteries, lithium ion batteries, and they're so good. These are Sony batteries. um, so yeah, so point is, I actually individually tried and tested each one of the MOSFETs and these resistors. I actually desoldered this one. So there was a capacitor that was burnt over here. You can see the desoldered ones over here, these two. One capacitor, one resistors. Those were burnt. So I actually desoldered it. It should have worked after, it still didn't, so I kept on going back into the trace where I can find the issue. I actually traversed, as I told you, right? I didn't know that because I actually traversed that entire pathway trying to figure out where in this entire loop it like burnt up. So turns out the battery circuit and the AC, they kind of misbehaved together and caused a surge that burnt up pretty much all the power circuitry in the power rails in the system end to end. So individual components I can still salvage, but the machine is not salvageable anymore. So that's why I'm like, otherwise I had planned to like make it in an IoT board, run some different kinds of, okay. Sorry, my display went off. The camera keeps on going off. Like I couldn't find out a solution for this. So I couldn't salvage this. I'm trying to salvage as much as possible from this system. And actually these MOSFETs are really good. I'll use them. Some of the chips are really good. So this one is HD audio. This one does the audio rendering over here. This is the audio coder. This one is most of the peripheral interfaces in the mouse, keyboard, the touch interface, like touch sensors, and all the other kind of stuff is actually happening in here. As I told you, so this one is the, I think I covered about the network and RF radio frequency, why it needs to be separated and stuff. So that is over here. This is the LAN, as in the modem essentially. The part is here, connected over. So you can actually technically you can break it up from here over here and take this out and use that as a standalone sorry so you can take this port along with this connector over here, break this part out, and use it as a separate um, modem, essentially standalone modem, that manner. If you have that spec and there's a data sheet for the things, right, you can do that. Anyway, so let's did we miss anything? We missed a lot of things, but did we cover enough? That's the question. Is there anything specific you want to know about, anything else, any other parts and stuff? Okay, cool, makes sense. So power is, as in the sense, there are 4 layers of power, right? So they're called S0 to S3, or no, actually there are S5 as well, but they're interleaved. So um, S0, S1, but then S3 and S5. I don't know about S2 and S4. So forget about the S. The point is, lower the power level is, that's how longer it is on. Okay, and how do you understand what that means? So if you put your system on sleep, when you're putting your system on sleep, the power is not out. In fact, the power cannot be out, then system cannot be on sleep. The RAM needs power to suspend the, keep the memory suspended. So the RAM needs power, but the processor doesn't. So those are the layers. So at which point you cut the power? And setting that up is the main. So on this motherboard, the power actually is not doing, when you ask the question that how is it ending up on my screen, I have to answer that in 2 parts. Power is separate, compute is separate. You cannot mix between the two. There is a signal that is going on between one, like from one to the other, and it's bidirectional. Like, it's not bidirectional, it's like there are 2 channels. One is saying, I am on, you can use me now. That is power on goods value. So if the power good is okay, then the system is allowed to start up. The actual hardware is now allowed to start the boot up sequence. So that's the power is saying, I'm working, I'm functional, I'm up. Go ahead and start the next phases. And at that point in time, only the S0, as in the lowest level power, that is up. And because that lowest level power is up, that's why you are able to send that signal that power is good. You can also have some of the laptops supports that, most of the desktop support that standby USB power. So even if the system is shut down, if it's connected with the SMPS, right, you can still charge mobiles and stuff from the USB port. So that's what happens also there. This is a standby power. Even before the system, as in the power supply, sends the power good signal, that standby power is always on. So that entire level, that plane is the lowest level of power. Once you send the power is good, then the next level of power wakes up. That's the power level where you start transforming power from one level to like the 18 volt that is coming in. Now you start breaking that down into different parts, different sections, and it goes in different like PMICs, like power management ICs. And those power management ICs are the ones mediating, or like the being the manager of or overseeing all the different power levels. They are saying that, okay, this particular set of our component does not need power yet. It's not at, we are not at S5 or S3 yet, so it doesn't need power. So when you send the power to S3, which is basically putting it sleep, right? That's the moment the power management IC for the CPU is saying that CPU doesn't need power, I'm going to turn it off at that point. Now, I can keep on going on these details. I just cannot figure out at which point it becomes boring for you. So stop me when it's like, okay, no, I understood whatever you're trying to tell. And if you're not getting some specific part, ask me about that as well. So there are different layers of power. Let's consider all the layers work up one after another. So it has to start from lowest layer to gradually the top level layer. When enable signal is sent on all of them, then you have the entire system up. Now software will work or not, that's a different story altogether. Not going to software part, but from hardware perspective, you are now enabled to run. I'll just cover the part that also it can go the other way around. Now the topmost layer can send a signal that I don't need power anymore, disable me, and it will go down that line. Like same, that's the way you send a shutdown signal or power down signal or a hibernation signal or whatever that is. So that's how it goes. So it is a bidirectional part. So one goes up, one bubbles down, falls down, precipitates down. Now once you have the whole system up, you forget about power now. Now we are talking about the firmware essentially. I cannot talk like there's entire this thing. I cannot talk about operating system level. Like I cannot come to the kernel level. Before kernel, they're just firmware, the BIOS and all the other kind of different ICs talking to each other over the signal that is basically sending 3.3 volt or 5 volt pulses to each other, right? So that's what is happening when they all get power. They have different needs. Let's say CPU got power, that's when everything basically starts. Everybody else already, so at the boot sequence, when you are trying to boot up CPU, so all the system got power at that time, you are allowed to boot. That's a post. When post happens, means all the components got power. Now what happens? Now the like the coming from top layer to now bottom layer happens. Now CPU goes ahead and asks everybody, are you up? Are you working? Are you functioning? Do you need to boot up? And all this, and reads configuration, all this stuff. So, and whether it needs to or wants to enable some device or not. Can it actually recognize the device while booting? Because it probably doesn't have it on the firmware. It cannot recognize it on the firmware. So it cannot enable that. Or it's disabled from BIOS and all this kind of stuff. It needs to look into that part and then wake those devices up. And waking up is nothing but sending, one of the pin is the enable pin, sending a high signal on that, or sometimes sending a low signal on that. Probably it's default high, sending a low signal on that tells that chip that I need to now start working, right? So when that happens, that sequence happens, either CPU is asking that, are you there? First sends the enable signal, and it is supposed to respond back in some certain manner. I'm just pointing at this chip. It actually is true for pretty much all the chips, right? So it sends like on enable pin, enable now. Once it is enabled, it is supposed to behave in a certain way. Through a different pin, it is supposed to send a 5001 or something other like that. So some of the acknowledgement, yeah, exactly, acknowledgement to tell that, okay, I am up and running now. You can use me, you can send me the things that I need to do. Once CPU gets that information, now it registers, okay, so now my wireless device is up. Now when the software requests me that I need to connect to a hotspot, now I can allow that to happen. Before that, you cannot try and connect to a network. If you try and that, the device not recognized, there is no network, or like your device there's no hardware that was recognized. Usually nowadays it happens so fast, all these things happen so fast, we do not actually get into that problem. We don't run into that issue anymore. But previously, when the things were much more chill, a lot slower, you could see that, like you booted into it, you're on your desktop, some of the devices still being recognized, the LAN, Windows XP LAN, there are two computer signal, and this is dot is going this way, that way, and it's trying to figure out whether they're connected or not and stuff like that. That used to happen. Nowadays it's so super fast, nobody cares. By the time the system is up and you're on desktop, the Wi-Fi is already up as well. So that is how it is happening. Display, same thing. Graphic card, it sends the signal to graphic card. Graphic card, are you there? Graphic card has a pin called presence. If you can go to PCIe pinout, you will see there's a pin called presence, and that presence pin is actually there for 1x, 4x, 8x, and 16x just before the last lane. So basically, that's how the system figures out whether it's a 1x card or a 4x card or 8x card or a 16x card or something like that, based on the location of the presence. Like, what's the last presence signal that I can find? So when it figures out, okay, there is a presence pin on a 16x lane on this PCIe, it says that, okay, which kind of card are you? Then it says that I'm a graphic card. Okay, cool, now I have a thing to display on the screen. And it, whatever CPU has, like, okay, now that you can handle the graphics, I'm gonna chill back, I'm not gonna process graphics. Whatever the graphic test comes in, I'm just gonna send that to you through the 16x lane over to you. I'll let you handle that part. I don't give a shit about graphic processing anymore, stuff like this. So this is in a nutshell. I'm trying to cover this up and go move on to the next one, next board. What should I cover? Raspberry Pi, I think. I was also trying to like that, or I can cover a mobile motherboard. It will be probably easier. So that's what I was saying, that if you have any other questions or something like that, let's clarify that part before I move on. Does that explain the question that you are asking? Okay. Um. Okay. Yeah. 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 So yeah. Okay, very good question. Actually, SoC I was gonna cover, but I will cover it in a better manner right about now. No, not different stream. It's I was going to cover it today only, but in a different section, different as in the next phase. Actually, because the thing is, I was going to, okay. Let's with that question. Let me move to the next part of the stream, because that's where I'm gonna address SoCs. Okay, so okay, this. Okay, what that is. This is a mobile phone. This is Galaxy, not Galaxy. This is Moto GS5, G5S. Okay, G5S, right. The part that you see covered in copper, right here, here, these are SoCs. This is the main computer, as in uh, the ARM processor and all this kind of stuff. These ones are basically the secondary part, like the power management and wireless capabilities, etc. All those things. This one, this camera, most likely, or the same model. Anyways, the point is, these are SoCs. How this is difficult to show in here. That's why I have it this in this place. If you can see, can you actually see properly? Okay. Do you see that the thickness is different from here to here? Because this is actually a different board that is put in over here. So this is a PCB on top of also on top of a PCB. It's a motherboard on top of motherboard, and that is soldered in. These sockets are soldered in. The very same way. Give me another moment. Let me see where is my recipe. So these are some Raspberry Pi Picos, the new ones that got released. You can say this is called castellated edges, right? These are solderable. So you can have a different motherboard. Let's say this is the motherboard. This is a slot free for the Pico. You put it there. You solder the edges on the same pins, and it's not a random spot. You have to choose the spot for that module, right? I'll explain why am I mentioning all these things, because these all things eventually thread back together. See this. This one is actually the same thing, similar thing as this, but without that module put in. So this is how it's expected to be initially. Then you put in this module, which is a SoC. This particular part is an SoC. It has a cover, but under that there is a chip, there is a timer, there is flash memory, and all the other kind of good stuff. So together, and the antenna. This is the antenna part. This is the keep out area. So you will not see any kind of traces or anything over there. Similar is marked as a keep out area. So you should not have any other kind of signal traces over here. And these are the solder points. So you can have the SoC, you can buy the SoC separately. I also have that. I can actually bring it here and show it to you. But anyway, so I digress. So effectively, when you're asking that nowadays, when you have too many SoCs, how are we going to use them or effectively isolate them in that manner? But the point I'm trying to make is that when you are going to use those SoCs, you have to abide by their rules anyway. And they will come with some rules, like for this ESP32, this is ESP32. And for ESP32, right, the rules are pretty obvious here. Do not keep traces under this section. Do not keep any traces under this section, and try not to keep any different traces other than these pinouts below this section. So you can actually have these section pinouts come and maybe pass through this area, or like route these ones through different ways, and maybe like whatever you want to do, like send it back. It's called via, how you want to call it. So you can send it back and use that pinout over here and put a different component on the back side and stuff. Just don't like take a pinout from here, take it back from here and take there. Like, do not do those things. Just keep this area within these pins configuration. That's what they ask. So if you are trying to use that ESP32 module over here, the SoC over here, you have to play by their rules and you have to implement it that way. So it doesn't matter Apple M1 or whatever other SoC you're planning to use. Whenever you want to use that, you have to go read their datasheet. Let me show how a datasheet looks like, how a nice datasheet looks like. Because I'm gonna show the Raspberry Pi Pico's datasheet. Okay, cool. All right, let's increase the size. This is a PDF. Almost all the time, the what do you call it? The data sheets are PDFs, right? It's also product brief. It's not a full data sheet, but this is easier to follow. But now that we have, this is let's say this is a light version. This is a lightweight version of data sheet. It has the specification, what you can do with it. It has all the footprint. So if you want to put it on a different motherboard, right, it shows you what's the measurement of which parts, how you can put it on a different motherboard, how much space you want to allocate for this to put this thing, and so that you can solder these pins, which pin which pin does what, and all this stuff are in a different shape. Let's see, this one, yeah, this one is it. So this is the full data sheet. You can see it's very long, but it has all the details about it, like these are the pinouts. I am going to increase the size so that you can have a better understanding over here. So how you are going to use it? Are you going to use it for SPI connection? Then these are the connections that you are going to use. Are you going to use UART? These are the connections that you use, right? This is the power plane. So this is where the 3.3 volt output is, like you can take output and you can send physis, the system voltage through here, 5 volt, and all the other kind of stuff. So it says all the things that you need to know about the pin configuration. This is the debug pins and all. Now this is not it, this is the start, this is just the beginning. Now that you know that, okay, each of those pins that you can see, they have their specific purposes. Now let's move on to the latter section, and then the mechanical specification, similar stuff that you have seen before, another part, but in much more detail, much more in depth, it goes in. And now that should give you a better understanding if you want to work with an what do you call it, an SoC, how much of their own document you have to refer back to and take in information from in order to incorporate that. You cannot just put in and like drop it there. That doesn't work. So you have to like consult with the datasheet a lot to be able to do that. And when you make sure that happens, like when you have been through all that, you kind of enabled yourself to use that product without interfering others, because all the SoCs will tell you that this is, if you want to use this product, these are the things you should do and these are the things you cannot do. If you abide by that rule, it should work for you. So that's how you want to keep out area. Like they could put things together, they didn't, because that's how you are trying to block the signal, noise, etc., all this kind of stuff, right? So these are the things that are happening. Different kind of chips have different kind of rules and restrictions, but yeah, some things are similar for most of them. Okay, I hope that somewhat addresses your question. Did you have any other part? Like, did your question have anything about putting the chip over here versus on top in a different manner? Because that also matters. If you put cards like the way graphic cards are mounted vertically, that pretty much makes that the noises don't pass through. Like noises caused in one board, one daughter card, do not actually go in the other daughter card, except for the traces that are running through them. So that's actually a better way. I'm pretty sure with the hey man, okay, bye. I think both of you are using the same account or something. I don't know. Uh, oh, not both. So Gautam is saying bye to Aniket and Sumit. I didn't even know Aniket was here. Hi Aniket. I'm sorry, man. I didn't know when you started watching. Anyway, so I'm actually not checking Discord at all. I probably should. It's fine. I didn't invite Aniket. I did. I did. It's cool. It's cool. Fine. So the point I was trying to make is, oh, he just joined. You missed a lot of parts. I'm not like it's impossible for me to go through all of that thing. Anyway, so please let's continue from over here. What I was talking about, I forgot. Can I? Yeah. So how do you know? So with the advent of newer generation of very really high speed connections, and that includes USB spec, that includes the PCIe Gen 5 and Gen 6 specs, and all this other kind of stuff. It is technically becoming impossible to buy Gautam. Thanks for watching, man. Who is silent? Oh, he is silent. Aniket is silent. So it's becoming technically impossible to run the traces in the planar manner, like the way we are accustomed to seeing motherboards. It will start becoming very, very different in future. the way M.2 drives are being mounted, the way graphic cards are being mounted, that will start becoming more normal thing to happen. There will be more of those daughter card mounting mechanism instead of giving like putting more stuff on the board itself, especially the high speed communication channels or high speed data lines or stuff. So yeah, SoC is like a blurred boundary. Any kind of module that you can think of that serves a particular purpose and that you can use and mount on a different board or something, you can call that an SoC for that other board. So in a sense, graphic card is an SoC, no matter how big that is. It's basically a system on chip that you can put slot in your motherboard, and now it does a specific thing, even though it does not work the exact same way. The x86 64-bit, it doesn't talk the exact same thing. It has some communication interface understanding over the 16x PCIe lane. That's good enough. That's what it is doing. All right. So with that said, SoCs, mobile motherboard. I talked about the reusability part of a mobile in last stream. I don't think you have seen that, but I have the videos up on YouTube if you want to watch that. Yeah, so let's move on to, I'm not going to go into that part. I'm just going to keep the discussion only within the scope of the motherboard discussion. So because but one point I do want to touch is that we did discuss that mobiles are meant or built in a way they are not meant to be repurposed. They are not meant to be reused for different things or broken down into different components and continue using. They are meant to be used, thrown out, and buying a new one. That's the ecosystem they have set up, and they have optimized for it. So as you can see, if you do not have too many custom components, the reason in a bigger motherboard you have seen so many inductors, so many capacitors, so many smaller resistors and stuff, the passive components and all, because you're taking a general purpose thing, then you are adding these capacitors, resistors, inductors, etc., to tune it to the specific thing that you want to work it at which point. You do not have those things baked in to one system, right? That makes the entire system, the entire design bigger, but it keeps it flexible. If you want to, like, if one capacitor burns out, you can change that capacitor and things will start working again. If you make everything an integrated circuit, and that's what the ICs are doing. These are all ICs, right? So ICs integrated circuit, what they're doing, they're basically combining multiple tasks together in one place under one umbrella. So when you're saying SoCs, when you're looking at the ICs, these are the grandparent of SoCs. These are also SoC, system on chip. The integrated circuit, they are also another circuit board mounted on top of another circuit board. Yeah. Okay. So, and they also have the similar kind of pin configurations. If you can see, this is really small and fine pitch, but and it might not focus properly. But you can see there are pins over here, 32 pins. Sorry, yeah, 32 pins. So in that manner, so inside this upper layer, whatever the black thing you're seeing, there are circuits inside, multiple different circuits. They're meant for doing one specific thing, not different things, right? In this board, you've seen that, let's say you take a MOSFET that is supposed to work from 2 volt to 30 volt range, and now you're saying no, I am going to use this particular voltage divider resistor, two resistors, divide the voltage and take it from here, so the IC knows I need to operate at 5 volt. You do not need to do those things in here. You, as a mobile vendor, you tell the the SoC maker that I want to work at 5 voltage, and that's how the specific. And when they know that we need to work on that particular thing, they don't need to create have resistors to divide the voltage. They can just make the IC in a way, or the MOSFET in a way, it only works within that 4.5 to 5.5 range, because it has to work at 5 voltage, right? So in that sense, if they cut down on all the bullshit, they come up with a very small solution. That's what you're seeing in here. Mobile motherboard is actually very free. There's not a lot going on in here. The only problem that is going on is all the APC and these board-to-board connectors. Here is one, here's the display one, and the camera one and stuff. This is the SD card and SIM card connection that is coming in. The audio, the speaker, and so sorry, this is the camera, speaker is here, and the battery inputs, battery power management, and the battery is actually the one that is taking up the most of the circuit. So this entire thing is pretty much optimized to not be reused. Almost none of it you can reuse, except for the battery, which you can very definitely reuse. I'm going to show that as in any of the next stream or something. So that's mobile. It sucks that this camera is really good camera, but if the mobile dies, can you reuse it? No, you have to throw it away. The particular port that it uses is completely, you cannot connect it. That is between the manufacturer of the camera and the manufacturer of the mobile. They only know which one of those pins do, and you cannot just create a same form factor pin and put it there, put the camera there, and expect it to work. The reason standards like USB or PCIe or M.2, those are standards, is because if one vendor says this is M.2 and another vendor says M.2, you can slot them into the same card and it will work. The reason these things are problematic in mobile, most of the mobile peripherals are problematic, is because they don't have any standard. There's just one off between that particular specific model between the vendor and the consumer in this layer is done for. So you cannot slot things in from here to there. This is a stark contrast between the PC motherboard that I talked about, where there is pretty much everything has a standard specification. You can term them by name, like this is this kind of connector, this is that kind of connector. Here they have no name. They're pretty much they're called board-to-board connectors or the flat cable connectors. That's it. But they have no specific, you cannot, by saying that, you cannot say that this is particular, is whether this data or video or whatever that is. No standard whatsoever. Okay. Now moving on to, let's open the LiveStream. Where is the LiveStream? And just take out the JSON. Okay, so I think I will come back to this because I opened the ESP32 anyway. Let's go on top of this as well. So this is a very small module for Internet of Things. This is not a computer. This is inside this, there is no micro processing unit, MPUs. Inside this, there's a microcontroller unit. And what's the difference between those two is that microprocessors have a memory manager, essentially on top of which you can write kernel, you can write more general purpose applications, and they would run more general purpose software on top of them. For MCUs, you have to run very specific firmware or ROM that they will know, and then only that they can execute. You can call they're dumber. They're a lot dumber, but they can do specific thing well and while costing much less. Give me a I'm sorry. So this module costs like 500 bucks. Actually no, this actually costs about 1,000 bucks, 800 plus rupees INR. That's quite a lot. But what does it do? So apart from the fact that it has a microprocessor, and you can see that it has a Wi-Fi, sorry, the antenna, that means it has wireless communication. It actually has camera and an SD card, and this thing is capable of a whole lot of different things, and you can tell it to, okay, if right now it's flashed with a custom program that like I flash it with that is, it takes one picture every second and saves it on this SD card. And if you take those, after that, once it is done, you can take all those images and stitch it into a video. You can create a 30x time-lapse video, right? So you can just put it over there. It takes almost no power at all. So it ran for more than 2 hours on a battery that has been decommissioned since 2014. Like a mobile battery that is haven't been used since 2014. That battery powered it for more than 2 hours. It took all the videos, as in images of a 3D print that was going on over there. It took all the images. So it consumes very less power. It has a LED flash as well, so it can flash the image for illumination if required. This camera is not a high-end camera, but you can put a higher-end camera, as long as the interface is same. You can put 5. This is OV2640, so this is basically 2 megapixel camera, but you can put a 5 megapixel camera if you want. And then there are other pins as well. Open pins means they are not used for any purpose, but you can use them for other purposes if you want. So, and then you can control this whole interface, the taking picture, not taking picture, or even streaming the image, that whatever the camera is seeing, over Wi-Fi on my computer. So if I run it, I can actually probably try and show, okay, no, it's actually getting late. I want to kind of wrap it up. Maybe in the next stream, I'll show that again. I think I did show it in the last stream. So this actually, you can send the video signal through Wi-Fi to your computer. I can capture that with OBS and then show it on stream as well. So this is actually a very powerful module. It doesn't have, let's say, USB. It doesn't have PCIe, all the other kind of goodness that a Raspberry Pi does. Let's say this thing, but this one costs almost 5,000 euros, right? This one is much cheaper and gets a lot of stuff done. If you want to control, let's say, a door where it can see who is the person that is coming in, who is the one knocking, can send you the data over Wi-Fi so that you can monitor that from your, like, inside the room, wherever you want to be, and then tells you that, okay, there's an alarm that rings and this is the image of that person that is standing over there, and you can shout, okay, let him in. And then you can, it has the ADC controller, like sorry, analog to digital. So that means that you can take the audio signal in, analyze that. It actually can do facial recognition as well. You can analyze that and analyze that okay, let that person in. So it will open as in the start a relay, as in the electrical relay, that will open the gate latch so the other person can come in without you having to move or anything else as such. So those kind of things, it can do a lot of different things. Like, I'm just talking about one use case, right? So this kind of stuff, you can do those same similar things with this Raspberry Pi, but this one costs 1/5. Sometimes that is properly worth it, like totally worth it, if you want to do those kind of stuff. But where things like this shines, things like this shines in a little more general purpose stuff. Like, let's say if you want to create, okay, I'm going into different tangent now. I was thinking about Raspberry Pi board. To go into that tangent. Anyway, so I think this is kind of interesting. I will. So let's say you want to create a network attached storage system. You have 4 different, 2 or 4 hard disks, you want to put them on the USB, and now because it's running a Linux system, this is a processing. It has a processor, microprocessor, MPU, so you can run a Linux, or yeah, it does run on Linux. You can probably have a Windows ARM version as well. So you can run a proper operating system on this and can do higher level tasks with it. You can manage, control your network. You can monitor different smaller devices like this with this. This can be the master that monitors other stuff. Um, so yeah, now recently Raspberry Pi Foundation came up with Pico. So this is from the Raspberry Pi guys. They designed this particular microcontroller unit, and these pins are basically the broken out pins of this thing. And this is comparable to this in a manner. It's actually not comparable, it's weaker, but this has a specific focus purpose, and this is a lot cheaper than this as well. This costs 250 $300. This like one third of this one's price, right? But this is pretty powerful as well. If you want to control motor, servo, or gate, or quadcopter, and all this kind of stuff, you can do it with this. And this is much easier to program, whereas this one needs mostly C++. It can actually support other stuff, but it needs to be boiled down to like compiled into lower level stuff. This one can directly run with Python and all the good stuff. It can directly run circuit Python and a little bit higher level, more comfortable languages, but people would be wanting to use with. So let's go into this board. What is happening in here? This particular IC that you see here, this is actually converting the voltage from 5 volt to 3.3 volt, because microcontrollers and the circuit level, logic level, they don't want to use 5 volt. 3.3 volt is better for them. So this is actually taking in here, converting into 5.5 volt, that is powering the entire system. And this thing right over here is the oscillator. Oscillator as in, this is the one, something similar to CMOS on desktop PC, right? That sends a little bit different kind of signal, but this one sends a half-wave pulse at a very distinct frequency at like, let's say 240 megahertz or 160 megahertz or something like that. That tells the processor inside how to subdivide the time, to know that time. Otherwise, how do you make it memory aware, time aware? You have to say that every fourth pulse of this thing, this is X amount of nanoseconds or milliseconds or something like that. So that's how computer understands time. So oscillator is something that you're gonna see on every board pretty much. So this one has it integrated inside. Oscillator is something that will be pretty much on every microcontroller board. That is definitely is going to be there. But there's actually not much other than that. This is an SPI flash. This is the, you can call it the memory where you are programming it. External. It has something internal as well, and that's pretty much it. Everything else is just broken out. So the reason I'm explaining that is because this is how easy a microcontroller unit is if you can go into that low level and you want to use the broken out part. This is how the bare bone, very naked, very basic stuff looks like. Everything else, like, walk backwards to this motherboard now. The concept is very similar, the scale is different. It works on a different scale, higher level, but the logic behind it, the function behind it is very much similar. It is a compounded problem. This has a lot more of these things into this. So the entire point of me breaking down the PCB and motherboards of like trying to get into this was to try and convince the people watching, basically you in this thing. Zilit has Aniket has a question. I'm going to come and answer you that. Give me a moment. So the point was, try and convince that they are not different. Even though this looks much more complicated, the way I explained that part, the power and how the signals and all these things are handled, and those are exactly similar in here as well. And this is just physics, how it works. There's no magic involved, and the concept is very similar over here as well as it is over here. It's just sometimes you're looking at a earthworm, sometimes you're looking at one of the like a complex mammal, and it seems like, okay, this is so simple, this is so hard, they might be worlds apart. No, this is a like, from our perspective, right, that's an animal, that's an animal as well. Just the same thing. This is just more complicated, but exact same thing. Conceptually, more of it, just that. So that was the thing, that to break that fear factor, like making it easy enough that you shouldn't be scared of motherboards and stuff. So that was the main purpose. So go ahead and open out any of the motherboard old system that you have and try and go through them and try to understand which of the parts that you can figure out. How do you, like, now you can try and figure out which part of it is broken. Maybe you have enough idea now to figure out how to figure out uh, which part you're looking into and how to solve that problem. Whether sometimes it's actually better to have a non-functional, like let's say Wi-Fi is not working. If you just desolder that Wi-Fi chip, right, the PC might just work because now one particular hardware now is not giving failure signal. And Wi-Fi is one thing, you can pretty much go, that goes for anything. Like maybe you do not need audio in that system. If you, it would be better if that PC boots, I'm fine with that, I don't need audio on board. You can use it for IoT and different purposes. Just open up the audio IC, it will not it will now recognize that I don't have audio, and it probably would boot. That has happened. Anyways, so I'm gonna answer the question that Aniket asked. Is Intel's upsquared board kit interfaced with a Arduino Grove Pi board be a higher end use hardware for IoT purposes? I don't quite understand the question that you're asking. What is upsquared board kit interfaced? Intel upsquared board kit interfaced with Arduino Grove Pi. Like Grove is just a U. Arduino Grove Pi. Oh, are you saying that, okay, different, okay, the higher end use hardware for IoT purposes? Can you please simplify the question? I don't really understand. Are you saying that Intel is a very different thing here? Intel does not make much of a microcontroller units. Intel makes microprocessors for high performance computing, mostly desktop computing and stuff, not for IoT purposes. Are you saying that using IoT devices like this along with microcontrollers? Can you please rephrase the question so that I understand it? I don't quite understand what you're trying to say. You can write down longer question if you want to. Oh, you're saying that. Yeah, why not? Basically, if so, let's say, let me answer that question from a different perspective. It is not about what hardware that you're using, whether that's a microprocessor or microcontroller, how higher end hardware that is. It matters how you are using it. So you can create a mesh network out of this ESP32 boards as well. So these ESP32 boards, they can create a Wi-Fi hotspot as well as be the one to connect to another one. So you can create one ESP32 like setup that just does the communication, that can be over the internet as well, and sets up the Wi-Fi signal for others to connect to, and each of the different, like you can call it master slave or like the main minion, whatever you want to call it, the terminology you want to use, the others can then collect the data and send it to the main one. The main one can decide what to do with the data, which part of it to send, whether to log it down in a SD card or save it to a cloud storage or something like that. You can do that with this. The reason I'm saying giving that kind of example is because ideally you can do that with, you can make that master uh, Raspberry Pi, or you can that make that master a computer, the desktop computer that you're using. Is any one of those better than the other? If it serves your purpose, if it saves the thing on your cloud, or if it saves the thing as a file on your, wherever you want on an SD card, does it really matter? It's not about being good or being bad. It's about getting things done. If you can get the thing done without any extra cost or extra effort, then either solution is good. You do not need a specific kind of setup to make it good. And that's actually the bigger part of IoT, is that like leave all the common sense at the gate. It's actually better to start from not knowing much than to have previous understanding of stuff that stops you from doing things or trying out other things, because you know, okay, I know this thing does that, I should not be using that thing for this, right? So that actually stops in IoT space. Actually go break a break a leg, like try whatever you like your heart wants, because that's specifically the purpose of this. The moment you can't or don't want to do that is because when you have found out the solution and you have created a specific like custom PCB or custom um, solution kit for it, that's when you don't want to do experimentation anymore. But whenever you're doing IoT, that means you still do not have a dedicated solution. You still are wiring things together to make something that doesn't exist or doesn't exist at large consumer level, to make that thing work. If you watch Bitrumi's channel, or like there are lots of different good channels over there, he does make a lot of custom projects. Most of those things, like running a console in what do you call it, input controller with Arduino or ESP32 or something like that. So for that he needs to create a custom board or something so that he can interface it. The earlier phase is completely like connecting this wire to that wire kind of stuff. After, when the experimentation phase is over, you design a custom PCB and then get it fabricated, and then you have a solution that is consumer solution. That point you don't want to make you don't want to do experimentation. But the earlier phase, do experimentation. Do not go from a presumption, okay, this is better, that is not better, if my setup has to be this way. In fact, go break that convention and find out a newer, different approach of doing something. Intel up squared, I still don't understand, but I think you are meaning that a higher end system. In that case, not the answer straight cut, easier answer is not necessarily, but probably would be easier. If you want a master control panel which is more visually pleasing, or you want to make it with HTML, CSS, JavaScript for having a dashboard and stuff, and you can do that on a Windows or Linux better, then probably yeah, it will be better on a like desktop PC. But if you just want the thing to get done, like maybe dump something on the internet, like save it on a Google Drive or Amazon S3 storage or something like that, you can totally do it with a smaller board, and it will be cheaper. It will be much cheaper. Okay, cool. I think I stretched that answer way too far than we actually intended, but yeah, probably it's worth answering more than answering this. I don't actually know how much to answer most of the time. Sometimes I go into a tangent, keep on going, something. Exactly. I just figured out that today I have been having a good feedback, so I know when to stop, when not to go any further. Because you have been at least on a voice communication, right? So you have been telling, okay, I got that part. So and now I know that I don't need to stage that any further. But I do not have that from Aniket, so I am not getting any feedback. And because when you know something, you want to express that, because otherwise you feel like that's not a complete answer, you're not giving the complete answer, so you keep on expanding on that, at some point it's like crickets. It's like, hey, itna sannata kyun hai bhai? So that's when like, oh, yeah, okay. Probably that person got it already, and I'm just stretching it way too far. Anyways, so anything am I missing? I was supposed to do something that I didn't. I just figured that adding this Raspberry Pi and this thing doesn't, like the Jersey Nano doesn't add anything at this point. I have like completed both the like smaller end and the bigger end and something in between. Oh, by the way, one point I did want to mention that I forgot, but I touched it. So if you see the smaller boards, like the IoT boards, they have something common with the bigger thing, the complex thing. Is that the modularity and allowing people to, if you have the guts, go ahead and go nuts, essentially, right? So they're explicitly inviting for it, and this thing is like, I'm not stopping you from this, but there's highly likely that if you don't know what you're doing, you're gonna screw up. But then it's not stopping you from it. This thing in the middle, right, is actively stopping you from experimenting. It's like, do not do that. I don't want you to do that. I'm gonna give my best to stop you from doing that. That actually goes back, and this is a specific. I don't know whether you know about Tagore, Rabindranath Tagore, right? One Bengali poet. So he wrote like he so there's a particular section in his poetry. You missed a lot of stuff. You missed pretty much the entirety of it. I'm gonna close the stream in a bit, like in 5 minutes. By the way, hello and welcome. And the stream will be on YouTube, so if you want to, you can go and watch. Anyway, so the thing that he wrote is that I'm gonna say the Bengali version first, then move over to the English one. So, উত্তম নিশ্চিন্তে চলে অধমের সাথে, তিনিই মধ্যম যিনি চলেন তফাতে. So the excellent one, the topmost, the top dog, is fine, is not insecure about going with anybody, everybody, even the bottom person, like the least favorable one. So they kind of get along together well, they're fine. The most insecure ones, the people who are most stressed about their social status, where do I go, who do I go with, how do I do things, they are the people in the middle. Those people are the ones who are most concerned about stuff. The bottom people don't having much to lose, so they don't give a shit. The people on the top, don't they are not scared about losing because they actually actively want to give out. The people in the middle, they're the one most scared about, and that's what is like. I was trying to draw that boundary as in a margin along with this. So this is the middle. They're the one trying to actively be different, but part that is bottom at the bottom and the part that is on the top, they're fine. Like if you know what you're doing, go ahead and go nuts, fix me. I don't give a shit. Do whatever you want. These ones don't want. Anyway, so that's it for this stream. I hope it was kind of helpful for you guys at least. And thanks a lot, Sumit, for being here on voice. Appreciate it. It was really helpful. I would actually, from next stream, I would want to have more people on the voice as well. I'm also more thankful to you because you stayed up. I think it's 5:30. Oh no, sorry, it's about 7 in the morning for you. 8 in the morning for you. I'm so sorry, man. I hope you still find some sleep time to sleep. I don't know how your schedule is gonna go. Is it Sunday today for you now? Oh, so your Sunday just started. My Sunday is gonna end, so that's why I was a little more worried. But okay, fine. You have a Sunday, but still, I'm thankful that you stayed up to watch the stream. Um, I'm really glad to hear that. Yeah. So I would actually want to do more streams like this. Like I kind of figured out that gameplay streams are not really for me. I don't bring enough value doing that. I'm not a good player in any game, so to say, right? So it doesn't make sense. So it will be just a shitty stream. But here, at least I can add or maybe try and answer some questions that might be of use for other people. So that's how I'm gonna start doing that. And it's actually better to do it this way than go and make videos on it, or like even try to boil this whole thing down into 10 or 15 minutes or
You
stuff like
already
that.
said that.
Sorry?
You have already said that.
When? Today?
Yeah, last time.
Last time, that is fine.
You don't have to say the same thing every time.
No, you have to.
Why?
Uh, why do you think YouTubers say that, okay, like, share, and subscribe to this channel so every time? Because this is something that unless you make it clear to people, they are probably having a different expectation. Not everybody is watching at the same time, right? So that's why instead of making a consolidated video about these topics, I'm using this streaming mechanism to um, put the content forward, and that is getting recorded on YouTube and staying there as well, so that it can create that referability instead of having to go through that. And it is detailed enough that anybody who is looking into that information, they can choose to listen whatever part they want to choose to. The timestamp might be wrong right now. I will fix it afterwards because it starts from the last week's information and detail. So that's what happens. I will fix that YouTube video in a bit. So, anyways, again, thanks a lot to all of you. Again, the regular user base, Mahir, Sumit, Gautam, and Aniket. Thanks to all of you. Thanks for watching. If somebody else is watching, thanks to you as well. Next week, again, I'll come back. I post what I'm gonna have the stream about at that time. See you on the next time.